Welcome back for another video on properties of power series, where we're using different arithmetic operations to combine old power series into new power series. And in the final video on this section, we'll take a look at integrating and differentiating power series to create new power series. In this particular video, what we want to focus on is multiplication of two power series with an overlapping interval of convergence, at least on some part of their intervals of convergence. And we want to create a new power series based on the multiplication of the old power series. So just as we can add and subtract power series to get new ones or compose to get new ones, we can do this with multiplication. Now, the process can get long and rather complicated, so we're not going to do a lot of these. In fact, we're only going to do two. We multiply power series, though, in pretty much the same way that we would multiply two finite polynomials together. Like if you had a third degree polynomial times a third degree polynomial or a fourth degree polynomial, you would basically use the distributive property, and then you would gather like terms. All the constants would be together. All the x terms would be together, all the x squared terms would be together, all the x cubes would be together, and so forth. So we want to do pretty much the same thing. So let's take a look at these examples that we've got right here. If we start with two power series that are known to converge, and they have at least some overlap in their intervals of convergence, we can represent this basic one, c sub n x to the n, starting at n equals 0, with the infinite polynomial c sub 0 plus c1x plus c2x squared plus c3x cubed, and so on. And the second one, also a known power series, known to converge on some overlapping interval of convergence with the first one, starting again at n equals 0, can be defined as d sub 0 plus d1x plus d2x squared plus d3x cubed plus blah, 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 forever and ever. Okay, well, if we multiply these out, we should be able to use the distributive property and then gather our like terms. So basically, multiplying this power series by this power series should be the same thing as multiplying this infinite polynomial by this infinite polynomial. So I'm going to be multiplying the two infinite polynomials together. Now let me share my screen with you so that you can see more easily the subscripts on these particular multiplications. So now what we're looking at is the subscripts that we have here represented when we multiply those two infinite polynomials together. Now, think about the only way you could end up with a strictly constant term, no x factor attached. The only way that can happen is if you multiply c sub 0 by d sub 0. Those are the only two terms that don't have an x factor attached. So the constant term would be c sub 0, d sub 0. Now, how could we get terms that have the factor x to the first? Well, there's really only two ways to do that. I have to take a constant like c sub 0 and multiply it by d1x. That will give me x to the first. Or I have to take the d sub 0 and multiply it by c1x, right? So one of those two will give me terms that both have the factor x to the first. So I can represent that here as c sub 0 times d1, that one times the second term over there, and then the first term over there times the second term over here, c1 d0. Now we can continue this pattern to find all the ones that will have a factor of x squared, but we can get these in two different ways. I could take c sub 0 and I could multiply it by d2x squared. So that would give me c sub 0 d2 times x squared. Or I could take c1x and multiply by next term, which would be d1x. That would also give me an x squared. So I could have c1 times d1. Now there's one more way that I could do this. I could take the constant from the second infinite polynomial and multiply it by the squared term from the first. So that would be C2 times D sub 0, which would give me this one. Now we can continue in that fashion and we can get the coefficient for x cubed as well. Now, the reason I took it out 3 is that there's a pattern starting to develop, and you really need at least 3 to start seeing the pattern and predict what the next one is going to be. So let's take a look. The first two don't really give a good hint as to what's going on, but the second one does give you a hint, and the third one confirms the pattern. So it is going up in the subscripts for C, C0, C1, C2, and down in the subscripts for D, D2, D1, D0. And we see this repeated in the coefficient of x cubed, C0, then C1, then C2, then C3, and going down in the subscripts for D, D3, then D2, then D1, then D0. So based on that, we can predict what the coefficients for x to the fourth would be, which would basically start with C0, D4, plus C1, D3, plus C2, D2, plus C1, D3, plus C0, D4, all multiplied by x to the fourth, and so on. So we have a pattern going on here. And because we have a pattern, we can represent the pattern. So what we want to do is we want to create, in essence, another function, another power series. It's not a power series, another series based on those coefficients. It's not a power series because it doesn't have x raised to a power, but it is a series. So again, we're starting with two known power series that converge on some common interval of convergence. And when they converge to the functions f and g respectively, and we're going to define this new series, not a power series, just a series, to be this weird combination of the coefficients. It's increasing in terms of c and decreasing in terms of d. So this gives us the sum from k equals 0 to n of c sub k, d sub n minus k. So this is the way that it's going to work. So this is a representation for just the coefficients, all right? Then we can define the product of the two original power series to be the new power series where the coefficients are given by this series, h sub n, times x to the n. And in fact, by this theorem, this new power series, given by the product of the old ones, is going to converge to the product of the functions f and g to which the original two power series converged. And, very important, it converges on I, whatever that original overlapping interval of convergence is. So it does not change the interval of convergence. So it's more like multiplying by a constant or multiplying by a power of x. It is not like the substitution or the composition one, which can change the interval of convergence. Now, this power series, where the coefficients are given by h sub n, which is this series, times the power series x to the n, this is known as the Cauchy product of the two original series, c sub n x to the n and d sub n x to the n. Now, these are rather complicated problems. They're quite difficult. So instead of trying to write them by hand, which I thought would be too messy and probably take too long, I thought I would go ahead and write out clearly how to solve these particular types of problems. Again, they can get quite complicated because that h sub n, the coefficients, is itself a series. And so we'll have to figure out what that gives us. So we're starting in example 7 with the power series. We want to find the power series for f times g, with f and g both being the power series starting at 0 of x divided by 2 to the nth. Now, remember, we've done this one before, so we know what the interval of convergence is going to be. It's going to converge when x over 2 has a magnitude less than 1, which means the magnitude of x is less than 2. So we know what the interval of convergence of the original is. Now we want to figure out what would happen if we multiplied them together. And we also want to know what functions these represent. So again, we know that we're replacing x with x over 2. So we write the power series representation. It did start at 0. So it should have the power series representation 1 over 1 minus x. So this gives us 1 over 1 minus x over 2, which becomes 2 over 2 minus x. So what we're looking at then is multiplying f and g together, where both f and g are 2 divided by 2 minus x. So they're both that function. And again, we know that it converges provided the substituted factor is less than the original interval of convergence 1, which gives us the magnitude less than 2. So this gives us the interval of convergence -2 to 2. So f times g is going to be the product of 2 over 2 minus x times itself, which gives us 4 over magnitude or quantity 2 minus x squared between -2 and 2. So we know what the power series is going to converge to. So what we want to do here is we want to start with the original 2 power series forms of these functions. They're identical, so that we can identify what C sub n and D sub n are, so we can try to get an H sub n. All right, so we're starting with f and g, both given by this power series. Remember that we're trying to get it to match the power series form. So we separate the 1/2 from the x. So this gives us 1/2 to the n times x to the n, which means, since these functions are identical, the same power series, that both C sub n and D sub n are 1/2 raised to the nth power, or 1 over 2 to the nth. You could write it that way as well. So now we define what H sub n is. And let's go back up to the theorem so that we can remember what H sub n is given to us. H sub n, remember that we're going up in the first coefficient and down in the second. So it's C sub k, D sub n minus k. All right. So back to example 7. We now want to find H sub n. So we've defined C sub n and D sub n as 1/2 to the n. And we know that H sub n has to follow this pattern. So that means that we have 1/2 to the k times 1/2 to the n minus k. That's what H sub n is equal to, the product of C sub k, D sub n minus k. But these both have the same base, 1/2. And since they have the same base, which is 1/2, we can add the powers. So k plus n minus k just gives us n. So H sub n is the series 1/2 to the n, starting at k equals 0 and going to n. In the last representation, though, notice that this value of the summand depends on n, but it does not depend on the index of summation, which is k. Because it depends on n, which is assumed for now to be some constant, whenever it's used, it's a constant value, it's changing, but it's constant each time, then we can take this out of that power series. The only thing that can't come out of the summand is something that depends on the index of summation, which is k. And this doesn't depend on k. So we can pull it out, and what it leaves behind, of course, is its coefficient, which is a +1. So we get 1/2 to the nth power times the series from k equals 0 to n of 1. Now, we know from our work on series previously that if the subscript, if the lower index of summation started at 1, then the series from 1 to n of 1 is n times 1, which is n. But that doesn't start at 1, it starts at 0. So we want to rewrite that one in terms of something that starts at 1. So what we do is we take the series starting at k equals 0 to n of 1. And that means that when k is 0, it's 1. When k is 1, it's still 1. When k is 2, it's 1. When k is 3, it's 1. It's always 1 until you reach k equal to n. So when k is 0, we get 1 plus the series from k equal 1 to n, which we know has value n. So the series starting at k equals 0 must be 1 plus n. Okay, now, what does that mean? That means that h sub n, which is this series from 0 to n of 1/2 to the n, can be represented as 1/2 to the n times n plus 1. This is its representation, all right, in terms of a function. All right, so now what are we going to do with this h sub n? All right, we're going to take this h sub n and we're going to substitute it into what we did for f times g. Remember, f times g was the function times itself, 2 over 2 minus x, which gave us 4 over 2 minus x quantity squared. And this has to be the power series representation of the product, which is from 0 to infinity, h sub n x to the n. Now, h sub n we found up here can be represented as 1/2 to the n times n plus 1. So we replace h sub n with what it's equal to, 1/2 to the n times n plus 1 times x to the n. Now, can we represent this in a slightly different way? Yes, both the 1/2 and the x are raised to the nth power, so we can combine them together. And you can write this as the series from 0 to infinity of x over 2 to the n times n plus 1. And again, the interval of convergence is between -2 and 2. Now, let's make a note of what would have happened had the series started at n equal 1 instead of at n equals 0. Then we would either have had to determine what the series x to the n converged to from a first over 1 minus r, and then use, oops, I've got a typo here. This should be from n equals 0, x to the n is 1 minus 1, or 1 over 1 minus x. Or you would have to manipulate the subscripts to start at 0. If you want to use the basic power series, which gives you the function 1 over 1 minus x, then the subscripts have to start at 0. If they don't start at 0, it converges to a different function given by a first over 1 minus r. And the series starting at n equal 1, we saw previously in the last video, would converge to x over 1 minus x. It would result in a different looking power series, and it might affect the interval of convergence as well, though I'm not sure it would. I think it probably would not, all right? So we have to be careful with where the power series is starting. If it's not starting at 0, then it won't be converging to 1 over 1 minus x, and we'll have to manipulate things. Most of the time, I think it's easier for students to manipulate the subscripts so that it does start at n equals 0, so you can use the function 1 over 1 minus x. This is a simpler function to use, and it's not terribly difficult to manipulate the lower index of summation. You simply subtract 1 from that, and in the summand, you replace n with n plus 1. All right, we want to work through one more example with multiplication. This would be example number 8. In example 8, we're again asked to find the power series of f times g, given that f is the power series 2 times the series x to the n, and g is the power series n times x to the n. Now notice that f can be written in strictly geometric form. You've got a constant 2 times something determined by x raised to the nth power. So this one is strictly geometric form, so we know it will converge to whenever we have magnitude of x less than 1. G of x, however, has this factor n. and it can't be part of the base, and it's not part of a common ratio. So this second one doesn't follow the pattern of a strictly geometric series. All right, so what we're going to do is we're going to have to take each of the series and identify C sub n and D sub n, and then we're going to have to find where they converge. Now, the first one we'll be able to use geometric series. Well, we've already talked through it. It's going to be magnitude of x less than 1. But what do we have to use whenever the series can't be written in strictly geometric form? Go back to section 6.1. Do you remember? The ratio test, right? So we may have to use the ratio test. So let's take a look at f of x. The 2 is a constant. We know the power series converges, so we can pull the 2 on the inside, which means that C sub n is always the number 2. Every C sub n is 2. They're all 2, all right? When we look at the power series for G, the series from 0 to infinity of n times x to the n, D sub n is given by n. Now, that's going to change depending on what n is, all right? So we can define h sub n in the following way. So again, we're going up in the coefficients of C and down, not coefficients, in the subscripts of C and down in the subscripts of D. But in our case, of course, this gives us the formula C sub k, D sub n minus k. All of our C sub n's, all of our C sub k's are 2. So we replace that with 2. Now the D sub n's depend on the index. So they're n if that's what the index is. If the index is k, then they're k. So this gives us the series from 0 to n of 2 times k. And again, we know this converges from what we have done previously back in chapter 5 with series. We can factor the 2 out, and we know if this started at 1, that it has a formula, n times n plus 1 over 2. It converges to that. So we want to rewrite this in terms of something plus the series starting at 1. Well, the first value, when you let k be 0, is 0. So this value right here is when k equals 0. And that's basically h sub 0. Right? So notice that that does not affect anything. So we can essentially rewrite this as 2 times the series from 1 to n of k. Well, we know the series from 1 to n of k, where k is the index of summation, has a converging formula of n times n plus 1 over 2. The 2's will cancel, so you get n times n plus 1. But don't forget that that means that h sub 0 was 0. So now we want to go back and we want to rewrite what f times g is, and we're using our formula right here, h sub n times x to the nth power. Now we're going to use our formula for h sub n. So notice we had to take the power series, or not power series, the series representation for h to n and write it in terms of a formula. We can't leave it as a series. It's got to be some formula dependent on the index of summation. So we replace h sub n with n times n plus 1, noting that h sub 0 is 0, and then multiply it by the power series factor, x to the n. So again, our h sub 0 was 0, so we can change the lower index of summation from being n equals 0 to being n equal 1, because the first one's going to 0 out and be gone. So now we have a power series for f times g starting at 1 and going to infinity of n plus 1 x to the n. Now we want to find the interval of convergence. So we need to find the intervals of convergence of both f of x and g of x. And then we have to find where they overlap. We know that when we have a product, that it keeps that same interval of convergence of what the originals had in common. But we don't know what the originals had, and we don't know what they had in common. So we've got to find that. Now, the interval of convergence for f of x is just going to be the magnitude of x less than 1 because it's geometric. Let's go back up here to the original statement when you're looking at this. This is a geometric series with a constant coefficient of 2. And so we know it's going to converge for magnitude of x less than 1. Now, the other series that we're looking at, this one, cannot be written in strictly geometric form. It doesn't follow that pattern where you multiply by something involving x every time to get from one to the next to the next. And that's because of the n factor, right? Still a power series, but it's not a strictly geometric power series. So what we do for that one, of course, is apply the ratio test, since it can't be written in purely geometric form. Remember, we're looking for rho. When rho is less than 1, we know it'll converge. It has the same condition for convergence as the geometric series. So we take the limit as the index of summation goes to infinity of a sub n plus 1 over a sub n in absolute value. Again, we're looking for absolute convergence. So we're going to take our series. So let me scroll down a little bit. Or actually, that's not going to work. So let me see if I can copy this off and I'll paste it down below. Okay, so I've pasted what f of x times g of x is. It's the series from 1 to infinity of n times n plus 1 times x to the n. And again, h sub 0 is 0. That's why we're starting at 1. So then I apply the ratio test with the sum ends being the value or the formula for a sub n. So I replace in here my n with n plus 1. And then, oops, hang on a second. It looks like I have an error. So let me fix that real fast and I'll be right back. Okay, I'm glad I caught that error. It doesn't change the value of the limit, but it would look wrong because I forgot about the n plus 1 factor that was in the expression for the power series. So this is our power series. Remember that h sub 0 is 0 for so the first term drops out. And then we apply the ratio test. So we have the ratio of a n plus 1 over a sub n. So we replace n with n plus 1. We replace that n with n plus 1, still plus 1. So that becomes n plus 2 times x to the n plus 1 divided by what we have in the original sum end, which is a sub n. Now the n plus 1's cancel, and then I'm going to get n plus 2 over n, and then I can rewrite x to the n plus 1 as x to the n times x, so the x to the n's cancel, and I'm left with the limit as n goes to infinity of n plus 2 times the x divided by n. Now x doesn't depend on that index of summation. It doesn't depend on n, so I can pull the x out of the limit, but it has to stay in absolute values because we don't know if it's positive or negative. Now, the limit of n plus 2 over n has form infinity over infinity. It's indeterminate. We can apply L'Hopital's rule, which gives us the limit of 1 over 1, which is the limit 1. And thus we get that the value of rho is the magnitude of x, or the absolute value of x. Now we know that the ratio test converges as long as rho is less than 1, so it will converge as long as the magnitude of x is less than 1. Now, because this came from the ratio test, we have to check the endpoints. We don't know for sure, like we do with the geometric, that it doesn't include them. It could. So we're going to check the left and right endpoints in the original series. And the original series is the one you see up here, n times n plus 1 x to the n. So now, if I'm looking at this one, I'm looking at, well, not this one. I'm looking at G, this one, n times x to the n. That's the original function we're looking at. Okay, so I plug in the left and right endpoints separately, but the first one at the left endpoint gives me an alternating series, but it's alternating and it has an n in it, which means that it's going to start with 0. And then when n is 1, I'm going to have negative 1. And then when n is 2, I'm going to have positive 2. And then I'm going to have negative 3, and then positive 4, negative 5, positive 6. So it's alternating, but the values are getting larger. So the even and odd terms, if you look at those sequences, they're each blowing up to either infinity or negative infinity. And because the sequence of the even terms and the sequence of the odd terms both blow to infinity or negative infinity, then we say that the sequence does not go to 0. So it diverges by the divergence test. The second one is even easier because 1 to a finite power, n, is 1. So we get the series from 0 to infinity of n. So the series becomes 0 plus 1 plus 2 plus 3 plus 4 plus 5 forever. And we know that the limit of that sequence of terms goes to infinity, which is not 0. So again, it diverges by the divergence test, which means that the two functions f and g both share the same interval of convergence, -1 to 1, which will become the overlapping interval of convergence of the product as well. So let's kind of pull it all together into one statement here. We have that the product of f and g converges together into the power series starting at 1 to infinity of n times n plus 1 x to the n over the common interval of convergence from -1 to 1. Remember that h sub 0 was 0, which is why we have a change in the subscript here. Now, in the next video, what we're going to be doing is we're going to be looking at another way of combining power series to get new power series and doing something to functions to get new functions. What we're going to be looking at in the last video on this section is integrating term by term or differentiating term by term. And we'll have to see whether or not, like in multiplication, it doesn't affect the interval of convergence, or if it's more like what we saw in the first video on this section, when the substitution or composition could, but didn't always, change the interval of convergence. I hope you'll join me for the last video on this most difficult section. From there on, it's getting easier.